Excellent. Thank you so much for the invitation. It's a real pleasure to be here to tell you a little bit about how I like to engineer swarms across scales. So I'm fascinated by this flock of birds. Together they can do these beautiful, complex dances in the sky. And there's many features that I find interesting for real-world applications. So for example, if you keep adding birds to the flock continues to fly, so they can scale to huge numbers. If a bird falls to the ground, the whole flock doesn't crash, so they're also very robust to individual failure. And together they can do more than the sum of their parts. For example, they're better at avoiding predators as a collective than any of those individual birds. And we see examples of swarm intelligence all around us in nature. You might know about ants creating trails to your picnic table, or you might know that honeybees are quite good at making decisions. And actually now we know that bacteria are also quite good at making decisions. And so the challenge for me as a swarm engineer is very often I have a swarm behavior I want to achieve, for example, create trails, do decision making, but I don't know how to design the individual agents, because the way these swarm behaviors emerge is by every agent following simple rules, just looking at their local neighborhood, and that gives rise to these emergent behaviors. So if I were to take the bird from the sky and look at it, that would not tell me how these flocking dances emerge. So how do you go from these swarm behaviors to the individual rules? And we have different strategies. We could use bioinspiration, so sometimes biologists have studied these animals and can tell us what to do, and sometimes we use things like machine learning to automatically discover rules. So here's an example of flocking. So if you want to do flocking-like behaviors, there's 3 simple rules that you could follow that give you something that looks similar. I'm not saying that this is what the birds do, but it gives you flocking-like behaviors. So the first rule is every bird is attracted to its neighbors. And that makes sense because you want the flock to stay cohesive. But if that were the only rule, they would all collide. And so there's a second rule, which is that you're repulsed by your neighbors as well, and that allows you to space out. But if that were the only rule, every bird would fly away. And so there's a third rule as well, which is you align your heading to the heading of your neighboring birds, and those 3 rules give you flocking-like behaviors. And once you have them, and we do a lot of mathematical modeling to test these things, you can throw them on a swarm of flying robots. So here I'm behind the camera. This was work done in Switzerland. Here we're waiting for the experiment to start. They're actually bird-sized, so sometimes birds follow them. You can see 2 of them there. And these are the GPS trajectories. And it starts very messy, but over time, we end up in this circular topology. And so our robot dance is basically a circle that's going around this point in 0, 0, just following those simple rules. So we can now engineer swarms and put them out in the real world. But that was really it was only 10 robots. And in my mind, swarms needed to work in much, much larger numbers. And so that got me excited about the field of nanomedicine. So I spent 3 years in the laboratory over at MIT that made nanoparticles for cancer treatment. And these nanoparticles, because of their size, their nanometer size, much, much smaller than the size of a cell, they're quite good at leaking out of vessels into tumor tissue. And so that makes them interesting vehicles for the delivery of drugs to certain types of tumors. And these particles, they work in the 10 to the power 13. So that was the huge number that I was interested in. And on top of that, the particles that they could make in the lab came in many different sizes. They came in different shapes. This is an iron oxide nanoworm, for example. You could change the charge of the particle. You could change the material. Some of them reacted to lasers or to magnetic fields. You could decorate these particles with molecules that could then go and interact with molecules on the surface of cancer cells, receptors that are overexpressed. And you could load them with drugs, for example, that you could release in a more or less controlled fashion. So really, there's many knobs that you can turn on the design of these nanoparticles. And so if you start thinking, well, how on earth am I going to make my nanoparticles swarm? well, maybe the birds had a brain, or maybe it's all the bacteria, but the birds had a brain that was controlling how they were operating. The robots had a program, which is a program that I put on the robot. And in the case of the nanoparticles, it's how do you turn the knob on the design of these particles so that the collective of particles does what you want them to do once you inject them into the system. And there's many things that might be interesting from the swarm world that could be used in the field of cancer. So for example, could these particles make a decision about the state of the tumor and deliver the right drug? Could they synchronize the delivery of a drug, a little bit like fireflies synchronize their blinking? Could they optimize trails to certain areas of interest in these tumors? And it's not a completely crazy idea. So this here is work that was done in the laboratory where we had blue particles that came through the bloodstream, leaked out into the tumor, and these blue particles were made out of gold. So if you shine a laser on them, they vibrate, heat up, cause damage to the tumor tissue. And then we have these pink particles that were fatty bubbles, essentially with a drug in them. And these particles were decorated with a molecule that was good at sticking to the damage that was just created in that tumor. So a little bit like ants deposit chemicals for other ants to follow, these blue particles created a signal in the environment that the pink particles could then attach to. And you get a 40-fold increase in the amount of drug that reaches the tumor using these cooperating nanosystems. So this is just to show you how very, very simple models and thinking of huge numbers is really helpful. So here we're trying to make particles that leak out of a vessel and kill 20 cells deep. And there's two knobs that we turn. One is how big the particle is, which is the speed, and one is how sticky that particle is. Okay, this is the only graph that you'll see, but I think it's quite helpful. So one is how fast it is, and one is how sticky it is. And we want to kill 20 cells, which is dark red. So most particles do not kill 20 cells. And it's actually counterintuitive. For example, that square A was a particle that was really sticky. So the bioengineer designing it thought it was wonderful because the particle was great at sticking to cancer cells and so would kill cancer cells. But if you think of all the particles working together, well, once they leak out of the vessel, they all stick to the first cancer cell they encounter and never go deep into the tumor tissue. So the group behavior of all these particles working together was actually quite poor. And you get a whole variation of different group behaviors just turning those two knobs. And you can think of smarter strategies. For example, can you prevent them from sticking, let them go deep, and then take that shell off the particle so they get eaten up by cells? And it turns out that there are particles that do this, and you can show that they go deeper into tumor tissue. All right, so that was us thinking for 2 years about how we could be helpful in the field of nanomedicine, but we wanted to go a step further and explore more scenarios. So we created a game called NanoDoc that allows us to crowdsource the design of these nanoparticles. So on the right, you have scenarios, and on the left, the players can go and design different types of nanoparticles. And when they click inject, that goes back to our scientific simulator. So this is what we teach the crowd. We teach them about cancer cells. We teach them about healthy cells. You need healthy cells in these scenarios, otherwise the solution to every treatment is just to put loads of drug, and we want our treatments to be more specific. You can change the dosage and when you inject particles. You can combine particles like those blue and pink ones you saw before. You can change the speed of the particle. Some of these cancer cells have receptors on their surface, and you can use particles to detect those receptors. You can load the particles, and you can make smart materials where if something activates the particle, it releases something in its environment. And you can do self-assembly, so particles that get bigger, slow down, particles that break apart, speed up. And actually, if you're a roboticist, you take a step back and you start realizing that these particles, depending on how we turn the knobs, have the ability to somehow sense their environment, to put something in their environment. That thing they put in the environment could activate another particle, so all of a sudden we have communication. And because we can modify how they move, well, we have some control over the way they operate. So those are actually a lot of the building blocks that we used to use in the world of swarm robotics. And so we had people play this game. They became nanodocs as they learned the different skills of the game, and they could tweet those diplomas out. And we had around 180,000 simulations around the world of people helping us design nanoparticles in simulation. And now what we're doing, this is work by one of my PhD students, is taking all this data and using it to train a computer so that ideally we could give it a scenario. It would use that machine learning tool to automatically give us the right nanoparticle design. Basically a way to figure out how you design the individual agents to get that group behavior that you're looking for. So this is work in progress. It's quite inspired from AlphaGo. Do you know about AlphaGo, designed by DeepMind? In that they started by training on games that already existed, and then they had the computer play itself to do it automatically. So we're also thinking along those lines. Could we have the computer play itself so that we can automatically discover the right particles for a specific tumor scenario? And we play the game ourselves. For example, this is our attempt at doing ant-like trail formation between the upper left corner and the bottom right corner. And actually, we had rules from the ant community, but they don't work on nanoparticles because nanoparticles are much simpler. So we had to simplify and simplify and simplify the rules. And it turns out that we can get trail-like formations using rules that are much simpler than what we used to use in the robotics community, and I'll come back to that. And for everything that we do it in reality. So you saw the flying robots that we threw before. We also have part of our team that makes little tumors on a chip so that we can monitor where nanoparticles go under the microscope, because there really is no way to wrap your head around this. Either you need to model it or you need to see it. And I think these are really powerful tools for us to understand these complex systems. So here in green you have actual nanoparticles, and in red you have, this is our tumor-like tissue. Within red we have cell-like structures, and we basically watch for hours and hours as these particles penetrate that environment. And actually, going from the robot world with 10 robots to going down to the micro and the nanoscale made me realize that there's a whole wealth of challenges in the biomedical field that have to do with things working together, as we learned before. And so I'd love to use some of our tools at swarm engineering in other areas. So for example, is there something to learn from the ability of cancer cells to leave their primary tumor site and recruit themselves to metastatic sites? Is that a potential swarm behavior we could understand, but also control? And the control is the part that I like as the swarm engineer. Should we be looking at the immune system? Should we be looking at neurons and their ability to self-organize? And should we be looking at things like bacteria and their ability to work together to do things like create biofilms? And maybe there's something that we could do there in the front of antimicrobial resistance. And if you're interested, we're actually building a swarm arena for microbes right now. So you can come and chat with me a little bit later on if you have ideas of what bacteria we can put in there. So things at the micro and nano scale work in huge numbers, and these agents are relatively simple. So what happens when we go back to the world of robots? And can we make robots that operate at similar scales as those micro and nano systems? And so at the Bristol Robotics Laboratory, which is one of the biggest robot labs in Europe, actually, we have lots of robots. So we have 1,000 of these robots, and these are some more sophisticated ones on the top. We have 16 of those. But I'm going to focus on these ones. So these ones are called Kilowatts. Don't forget the O. They were originally designed over in Harvard, and actually the students in our lab built 1,000 of them. So we have the building blocks that we need for swarming. They have 2 vibrating motors, so we can control left, right, and straight, but the reality is it's very noisy, and so we don't have precise motion. They have at the back an ambient light sensor, so we can interact with these robots using light. They have infrared communication, so they can talk to their neighbors within 10 centimeters. And they have an LED, so we know what state these robots are in. So this here is maybe 100 or so robots pretending to be nanoparticles. So in green, you have our nanoparticle robots. In red, our cancer cell robots. When the cancer cell robots bind to the green robots, they eat them up with a certain probability and they become purple. And this is a case where the particles were very sticky, so they actually never go deep in this robotic tumor tissue. And this was quite interesting because there's lots of room for them to move, but just the nature of random motion causes them at some point to hit one of those two robotic cells. And so I show this to bioengineers sometimes because it looks a little bit like those green and red dots that you saw, which were actually things under the microscope. And they say, why doesn't your robot go there? And I say, well, why doesn't your nanoparticle go there? And so we need better tools to think about how these dynamic systems operate. But something that we realized is actually, do these robots tell you anything? And we wondered if we could make a robot version that was proportionally at scale to what we would see if we were to zoom into a tumor tissue. And so, if you take a nanoparticle, say it's 200 nanometers, and you blow that up to 3 centimeters, which is the size of our robot, that's a multiplication factor. And you do the same thing for the cell size. And so this here is basically a scenario that's proportionally at scale to what you would see if you could zoom into the tumor. And it turns out that the time is real time. So the speed at which these particles move through our robotic tissues corresponds to the speed at which they would move within the tiny tissue. So these are new playgrounds that we're exploring to understand things in a more visible way. But we're also thinking, okay, well, if we can make these robots work proportionally at scale, similar to the nano world, maybe we should think of huger numbers in the robot world. So if you take a farm field, there's 1 kilometer by 1 kilometer in that farm field, and there's around 100,000 seeds. So those are scales that are actually much closer to the biomedical world. And would it make sense to make 100,000 robot seeds that are biodegradable, just have enough nutrients for that specific seed, and go and plant themselves? Likewise, does it make sense to think of robots that might be helpful for water monitoring, and robots that, again, we would need to find new materials to make these robotic systems so that they are safe and biodegradable, but that might be able to go in a water source and light up in different ways depending on the pollutants that are present, and maybe even create trails to the sources. And you can think along those lines as well if you're thinking of disaster scenarios and how we can create trails in those environments. So this is really a different way of thinking of huge numbers, which frankly requires advances in the area of material science and a whole host of different areas to design these robots. But what's interesting is we can create the algorithms that work in those large numbers and that are a little bit closer to what we see in living systems, in biomedical systems as well. So here what you see is decision making with a swarm of 400 robots or so. So these robots here are deciding between blue or red. Blue is the correct decision, and you can see very quickly they converge. So blue and red here, and over time, they converge to blue. This is random motion. It's them just looking at their local neighborhood and adopting the opinion of one of their neighbors, but there's many different variants of this. And there's many ways you can make these more robust as well. So I skipped this slide, so let's try again. This here is 150 of our robots. So these are real robots, both of them. They're not simulations. And we're releasing them here, and they're looking for that robot at the upper right corner. So this is actually the algorithm we discovered in the nanoparticle simulator. This is sped up. They don't move this quick. I'd love for them to move this quick, but they don't. And let me just play that again. This is purely random. This is not the way you design an algorithm for robots, which is typically more deterministic. So this is random motion, but as soon as they find that second object, they basically send a signal saying, hey, I found that object just within their local neighborhood, and anyone who detects that stops and sends that signal, hey, we found the object. And you get these trails. And it looks like these trails find the nearest object. It looks like these trails are really good at avoiding obstacles and still finding the object that you're looking for. So actually, with random motion and very simple local interactions, we can do things like trail formation in huge numbers. And if you wait until December, I can't show it now, but we have a really new paper that takes inspiration from morphogenesis, so how we create shapes in organs, to use 350 robots to create shapes as well. So they grow limbs, and we can chop the limbs off, and they regrow, and they do lots of really interesting things. So keep an eye out for that. So really what we're trying to do is engineer swarms across scale. And the tools that we have are bioinspiration and things like machine learning to automatically discover the tools. And really what I'm finding is actually a lot of these systems, we've been thinking about them in silos, but there's a lot of similarities across them, and there's a lot to learn from the nano world to make better robots, but there's also a lot to learn from the controllability that we have in the robot world to see if we can improve things for biomedical applications at the nano and the micro scale. And if we're thinking a little bit about art, a lot of these swarms are beautiful as well. So just recently I was brainstorming with a student, and she was wondering if we could do swarm sculptures where the swarm robots are a material that we could go and sculpt. So I'd love to think as well about how the human has an input and a control of these systems so that we can make these beautiful flocking patterns, but in a way that we really control and understand what is emerging from them. So something that's worth mentioning is that everything that we do is very, very cross-disciplinary. And so the people who work with us are biologists, computer scientists, materials scientists, chemists, people from the biomedical front. And it's usually really fun to see how everyone has a different terminology for the same thing. But conferences like these make us understand that actually we're all working in a similar area. All right, thank you very much. And I'll be around a little bit to chat.